Hello all, in this lesson we are going to be starting our Unit 6, Formulas and Equations. We will be thinking about formulas as recipes in this lesson, but I'll also discuss just the concepts of molecules versus elements, and I'll introduce coefficients and subscripts formally for the first time. We do have a bookwork associated with this lesson. It's 1 through 6 on page 30. And we would have completed the look back for the Unit 5 exam. Please copy down these questions on loose leaf, and we'll do these in classwork tomorrow. And this is our aim today. How do we read chemical formulas? This should be listed on your classwork page as well. And you should also be starting a new essential questions handout. You can use the original handout that I gave you for the previous unit and adjust it to better fit your needs, or it could be an exact replica. But this will be the first aim that you would list on that handout. Okay, so we can think of formulas as recipes. Let's look at an example of a formula. So I've written one in for you here. It basically just says that sodium atoms plus chlorine gas, which has to have a subscript of 2 because it's a diatomic molecule, but sodium and chlorine gas would make sodium chloride. There are 2 sides to this reaction. The left-hand side is going to be called reactants, whereas the right-hand side is called products. During this reaction, the Na and the Cl combine to form the compound sodium chloride. I'm using the word chloride because chloride, or the ending IDE, indicates the negative ion of an atom. And the formula for this reaction is what I've written up here earlier. I'll just rewrite it. Now, if I were to put way too much Cl into the reaction, then you would run out of sodium before you could make all the sodium chloride. So if there's too much chlorine, you'd run out of sodium first, and you would get the normal amount of sodium chloride, but you would have a lot of leftover chlorine. And this gives us a really important vocabulary word for this unit, and that's called limiting reactant. So since you would run out of the sodium before the chlorine, then the sodium is what would limit the reaction, because there would be plenty of chlorine left over waiting to react with sodium, but it's all gone. So that's why sodium is the limiting reactant. You can see this also here in the cartoon version. What would happen if you put way too much sodium into the reaction? So here is my version of way too much sodium with just a little bit of chlorine. What you would get is a lot of leftover sodium, and chlorine would be the limiting reactant. So I was careful to say that there would be exactly 4 of the NaCl, and the way that I did that was I thought about which atom was going to limit the reaction. So the limiting reactant is the chlorine, because there's only 1, 2, 3, 4 atoms of chlorine. And so since there are only 4 chlorine atoms on the reactant side, it will be transformed into 4 compounds, each containing 1 chlorine. So this matches up, and that's why chlorines are a limiting reactant. But you would have leftover sodium, meaning maybe you would use 4 sodiums, these would be used, and then these would all be unused. All right, guys, and just for fun, I have a video here of sodium reacting with chlorine. All right, let's talk about molecules and elements. So usually we deal with reactions that involve molecules, compounds, and or single elements. What? So write observations of the reaction that occurs when we put hydrochloric acid, whose molecular formula is HCl, into a flask containing zinc, elemental symbol Zn.
The next reaction we have is zinc in hydrochloric acid. What do you think will happen? Okay, I have here a balloon. It's filled with zinc powder, and I'm going to put it over this flask, which is got hydrochloric acid in it, and mix the two together, which allows us to collect the gas that's produced. Here. We can light the balloon on fire.
So I included some observations that I noticed here, like that the zinc dissolved, the hydrogen gas was produced, and that hydrogen gas is also flammable. So we can use the zinc dissolves to answer this next bullet, what happened to the zinc. It dissolved because it was reacting with the chlorine from hydrochloric acid. So I can explain that a little bit better using an equation. And you'll see the equation here. It says that two hydrochloric acids will react with some number of zincs to produce hydrogen gas and zinc chloride. I will also draw in some sort of cartoon-style molecules on the right-hand side where they're missing to show you what is left over and what is used. So I started with the one that I was interested in first, which was the zinc chloride. I can see from the formula that it's 1 zinc and 2 chlorines. So I have 2 chlorines here, which means that I've used this chlorine and this chlorine. And I've also used 1 zinc. So I've used this zinc. But there's a lot of stuff that I haven't used. So these 2 hydrogens haven't been used. They bond together to make this hydrogen. So now I can account for these. So there's 1 hydrogen, another hydrogen, and here they are in the reactant side. So now I can see I've used up all of this, and I have this left over. That means that this is what I have in surplus. It's like extra stuff that I have left. So I'll write extra Zn. And it also means that zinc is not the limiting reagent. The limiting reagent is the one that runs out first. And in this case, I believe it would be the HCl as a whole is the limiting reagent because it is definitely all used up before the zinc is used up. All right, let's answer the question at the bottom. With what did the zinc react? Chlorine. We know for a fact that it reacted because new substances were formed, namely hydrogen gas. Secondly, how did the video show that hydrogen gas was produced? He did a flame test at the end, and hydrogen is highly combustible in the presence of oxygen. So since it caught on fire, that is evidence that it was hydrogen that was collected in the balloon. So in the reaction on the previous slide, we combined zinc with hydrochloric acid to make new compounds. And if I had put just a tiny amount of zinc in a gigantic ocean of HCl, I would have lots of leftover HCl. But if I put a tiny amount of HCl on a gigantic mountain of zinc, I would have lots of leftover zinc. So this ties in well with a discussion of coefficients in chemical equations. Coefficients in chemical equations are really important because they help show that atoms are not actually gained or lost during reactions, that they're all conserved. And they're also helping us to show that there won't be huge amounts of waste on either side of the reaction just because we're putting random amounts of things in. They really show the precise amounts of things. And, you know, as an example, I highlighted the 2 in front of this HCl. And that 2 is actually really important. It's saying that there are 2 molecules of HCl, but it's also, it's applying to the H and the Cl, of course. So it's saying that there are 2 atoms of hydrogen on the left. And if you come over to the right, you can see that there are only 2 atoms of hydrogen. So if we had left the 2 out of the HCl, it wouldn't be showing that there were equal amounts of hydrogen on the left and the right, which of course is true based on the law of conservation. And just to finish up here, the 2 applies to the Cl and the HCl as well. So there are 2 chloride atoms shown on the left, and on the right you should see 2 chloride atoms as well. They're right there. And this is an extremely important concept in chemistry, that these atoms are not gained and lost, so the coefficients are there to show that there are equal amounts of things on the left and the right-hand side of the arrow. Additionally, the use of coefficients in chemistry allow us to make predictions about the amount of products that will be produced through a reaction. For instance, what's the minimum number of zinc atoms needed to obtain 1 hydrogen molecule? So this is a hydrogen molecule, and I apparently needed only 1 zinc atom. Furthermore, if I were charged with producing 3 hydrogen molecules, that's triple the amount of product shown in the reaction, then I would need triple the amount of original zinc atoms. And that's just a law of ratios. If I need triple this, I need triple that. So one thing I'll point out here is that if I was asked for 1 hydrogen molecule, I needed 1 zinc. If I needed 3 hydrogens, I needed 3 zincs. That's a 1-to-1 ratio here and a 1-to-1 ratio here. And this also comes back to the original equation. I have 1 molecule of zinc, or 1 atom of zinc in the equation, and 1 molecule of hydrogen. So there's the 1-to-1 ratio that explains this answer as well as this one. So let's use that concept to answer this final question. What if I need 2 units of zinc chloride? So zinc to zinc chloride. When you come to the equation, you can see that each 1 atom of zinc will produce 1 unit of zinc chloride. So it's another 1-to-1 ratio, which means that 2 units of zinc chloride would require 2 atoms of zinc. 1-to-1 ratio. Okay, so here's a ridiculous made-up story that I wrote, but let's say that you had done an experiment that used 1 liter of hydrogen and 1 liter of oxygen, and when you combined them, you got just a ½ liter of oxygen remained, but a clear liquid was produced. This reaction would be the reaction that produces water, and the equation is shown here. One of the things you should be sensitive to at this point is that we have 2 hydrogen atoms on the left and 2 on the right, which is a good thing, but we have 2 oxygen atoms on the left and only 1 on the right, which is a bad thing. So I'm going to add some coefficients to make this balanced. So what I've done is I put a 2 in front of the H2 to give me 4 hydrogens on the left, and on the right I have a 2 in front of the H2O. The 2 will apply to the H as well as the O. That's how coefficients work. They apply to everything within the molecule after it. So I'm going to have 4 hydrogens, which is great, and 2 oxygens, which is perfect because I have 2 on the left as well. So subscripts are these little guys right here. And subscripts are showing the proper ratio of atoms in a bonded compound. And the coefficients, which we've been talking about for a while, they're really, in this invisible 1 and this 2, they're really just there to show you the ratios of molecules in a reaction. And both of them, therefore, are good at showing ratios. They're just showing ratios of different things. Subscripts are showing ratios for atoms, whereas coefficients show ratios for molecules. There is a little bit of a tricky subscript rule I'd like to point out, and it is easy to demonstrate using a molecule like this. So the subscript really only applies to the thing that directly precedes it. So this 2 is applying to iron. It means there are 2 iron atoms, but it doesn't mean anything to the right of the 2. So this 2 means there are 2 irons. And this 3 means that there are 3 of this. This is called a sulfate. So we have 3 sulfates, but the 3 means nothing for the iron. So this is just talking about the thing that directly precedes it. And likewise, this 4 is only applying to this oxygen. It does not apply to the sulfur because the sulfur does not directly precede the 4. So this 2 for this iron, this 4 for this oxygen and nothing else, and this 3 applies to the oxygen and the sulfur because of the parentheses. So there are 12 oxygen atoms in 1 unit of iron sulfate because there are 3 units of sulfate and each sulfate has 4 atoms of oxygen. And finally, we've made it to the pair-up. I am going to make some edits to these formulas so that they appear correctly for you to copy them down. So there are your formatting edits. Please copy down these questions in preparation for tomorrow's classwork. Likewise, please copy down the summary questions. I don't see any formatting errors, so you can copy these down as is. Good night, and thank you for watching.